What if I told you that a material exists that can float, completely frozen, locked in midair above a magnet? No strings. No tricks. Pure physics. This is quantum levitation, and it's one of the most mind-bending phenomena in all of science. It all starts with superconductors. These are special materials that, when cooled to extremely low temperatures, conduct electricity with absolutely zero resistance. No energy is lost. None. It's a perfect conductor. Superconductors have three defining properties. Zero electrical resistance, electricity flows forever with no loss. Perfect magnetic expulsion, magnetic fields are pushed completely out. And they only work at extreme cold, typically below negative 135 degrees Celsius. Here's where it gets fascinating. When a superconductor cools down, something extraordinary happens. It expels all magnetic fields from its interior. This is called the Meissner effect. The material doesn't just resist the magnet. It actively pushes it away. Visually, magnetic field lines that would normally pass through a material are instead pushed around and outside it. The magnet above has nowhere to go, so it floats. But the Meissner effect alone doesn't explain levitation fully. There's a second phenomenon at work, flux pinning. And this is the part that truly defies your intuition. In thin superconductors, tiny channels called flux tubes allow small amounts of magnetic field to pass through, but they lock in place. The superconductor is literally pinned to the magnetic field. It cannot move up. It cannot move down. It is frozen in space. So how do we actually make this happen? We take a superconducting ceramic disc made from materials like yttrium barium copper oxide. We pour liquid nitrogen over it, dropping its temperature to negative 196 degrees Celsius. Watch what happens next. Liquid nitrogen floods the disc. Cryogenic vapor fills the air. The material transitions from normal conductor to superconductor. Its internal structure reorganizes at the quantum level. The transformation is complete. And then, you place it on the magnet track. And it floats. Completely still. Perfectly locked. It won't fall down. It won't fly upward. It just hovers, pinned to the magnetic field at the exact height it was cooled. What makes this truly stunning is that it can float at any angle. Upside down. Tilted sideways. Even underneath the magnet track. Gravity is not defeated, it is balanced by the locked magnetic force. This isn't just a laboratory curiosity. Quantum levitation is the foundation of technologies that could reshape civilization. Magnetic levitation trains, maglev, already use superconducting principles to reach speeds over 600 kilometers per hour. Quantum computers use superconducting circuits to process information at speeds no silicon chip can match. MRI machines rely on superconducting magnets to generate the powerful fields needed to scan the human body. And lossless power transmission could one day eliminate energy waste in entire electrical grids. But there's a catch. Every superconductor we know requires extreme cold to work. The holy grail of physics, a material that superconducts at room temperature, has not yet been reliably achieved. Scientists around the world are racing to find it. In 1911, the first superconductor was discovered at just 4 Kelvin, nearly absolute zero. Over the past century, scientists have pushed critical temperatures higher and higher. In 2023, claims emerged of materials approaching room temperature, though peer review continues. At the quantum level, electrons inside a superconductor form something called Cooper pairs. Normally electrons repel each other. But at low temperatures, they pair up and move as a single quantum entity, flowing without any resistance whatsoever. Think about what this means. The floating disk you can see with your naked eye weighing several grams, spinning in mid-air, is the macroscale result of quantum effects happening at the scale of individual electrons. Quantum mechanics made visible. If room temperature superconductors are achieved, the world changes overnight. Hyperloop transport with zero friction. Quantum computers solving problems in seconds that would take classical computers millions of years. Power grids with zero energy loss. The physics is real. The applications are waiting. Quantum levitation isn't science fiction. It's science fact happening right now, in laboratories around the world. A disk floating frozen in mid-air, locked by quantum mechanics to an invisible magnetic field.